So let's talk real quickly about the bilinear, what a bilinear form is. So the weak form will contain two types of expressions. Those involving del u and those involving u, and those involving only del u. So you want to, what we're doing here, we want to group them, right? So that the terms in the weak form that have both del u and u, we're going to group them into one group, and the terms that only have del u, we'll group them into another group. Okay? So we're going to group them. So the ones that have both and the ones that only have del u. So we can then write, and you'll see this a lot in the mathematics literature. Or let's say the problem is stated as find u such that this is the variational problem. So in other words, I guess I should have said, given del u, find u. That should be del u. So given del u, find u such that this is true. And this is the variational problem. The functional b del u is said to be linear bilinear if it's linear with respect to each of its arguments. So the functional is said to be bilinear if it's linear with respect to each of its arguments. Okay? And in our model problem, this is true. You could go and verify that, the way we define B. And of course, it's symmetric. It's symmetric if BUV is equal to BVU. This is also true. You can go and verify that. Just plug in, we had del U and U, but if you swap them, U del U, it'd be the exact same function. Well, all right now we're just saying that B is bilinear, and we're trying to establish that B is bilinear and is symmetric. Okay, and for our model problem, that's true. You can verify both of those things. So I'm just giving you definitions for bilinear and symmetric. And so if that's true, if we have something that's bilinear and symmetric, then B del U is equal to 1/2 del B U, right? And we still have that, well, L del U is equal to del LU. And so now we're going back to our interpretation, and this is why I use the del operator the whole time. A lot of times in the math community, just instead of writing del U, they'll just write V. It's easier to write one thing than two. But all of this stems from the mathematics are all stemming from the calculus variations, and this is the reason I carried this around. If you remember when I introduced this del operator, I said it's just like a differential operator in that it commutes with the function. So here it's very easy to understand that, and then I in fact use it that way previously in the last lecture. Del of the variation of this function is the variation of the function del U, right? Okay. This may not be quite so clear, but we have seen it. We have seen it because we had that we used it before. We had d dx del U dx. And if you remember, the first thing I did was I took the variation of the integral. Of course, these goes from 0 to L. Of EA over 2 du dx squared. Go back and look at your notes. This is where we started. We had a term that looked like that, and I took the variation of that guy, and then you just, because of the way the variational operator commutes with the differential operator, you can use the chain rule, so you have 2 d del U dx du dx, right? And so that is equivalent to that. Therefore, then if this is that, then it's also that. 1/2 BUU, which is what we have here. Okay? So then we can rewrite the bilinear. Just one more last thing here. So we had that the bilinear form was B del U equal L del U, right? Of course, that's also B del U minus L del U equals 0. And by what we just established with respect to the bilinear, we can also rewrite that as 1/2 del B U minus del L U. we're going to define this as some quadratic functional I, or rather del I, that's equal to u. And of course we know that has a stationary value when it's equal to 0, right? So we can restate the variational problem as minimizing a functional IU 1/2 BU U minus LU. All right. So we'll really pick up from here next time with what the Ritz method uses. The Ritz method actually minimizes this quadratic functional. This quadratic functional is inferred from the weak form or the bilinear form. Okay. Now you can show that the solution to the bilinear form is also the minimization of the quadratic functional. They're equivalent, right? So when we'll go ahead and show it next time for Ritz method, where we'll actually minimize a functional that looks like this for our model problem. And then when we go on to the finite element method, we're just going to simply solve the bilinear form. But they're equivalent to one another.